Hey everyone. Seems like you've stumbled upon something pretty interesting, this star attention algorithm.
Yeah, it's got a lot of people talking.
It does. I'm seeing a ton of articles here and papers. Looks like you're really digging into how LLMs are tackling these massive amounts of information.
Definitely. It's a huge challenge right now, especially with these new LLMs like Gemini and Claude that are handling millions of tokens.
It's mind-blowing how much these models can process now, but it's also got to be incredibly resource intensive with that traditional self-attention mechanism.
Exactly, and that quadratic complexity just doesn't scale efficiently. You run into bottlenecks pretty quickly.
That's what I keep seeing in these articles.
Yeah.
Everyone's looking for a way to get that long context processing without sacrificing speed or accuracy.
Right. And there have been some interesting attempts like flash attention, which works really well on GPUs, or ring attention, which distributes the workload.
But I imagine those approaches come with their own trade-offs.
They do. Every solution so far has some limitations. Even things like KV cache compression, which tries to be more memory efficient, you're still making compromises.
So this star attention algorithm claims to have cracked the code with this two-phase approach, context encoding and query encoding. It almost sounds too good to be true.
Well, let's break it down and see how it works. The first phase, context encoding, is all about dividing that massive context into smaller chunks and assigning each chunk to a dedicated host.
So kind of like breaking down a complex problem into smaller, more manageable pieces.
Exactly. Each host becomes an expert on its assigned section, building up this localized understanding of the information.
That makes sense. But how do you make sure the model doesn't lose sight of the big picture when you've got all these separate hosts working independently?
That's where the second phase comes in query encoding and token generation. Your query, which is usually much shorter than the overall context, is sent to all the hosts simultaneously.
So they're all working with the same question, but focusing on their specific area of expertise.
Precisely. Each host processes the query through the lens of its local knowledge and generates a partial response.
It's like having a team of specialized researchers. Each one analyzes a different chapter of a book, and then they pool their insights to answer a specific question.
That's a great analogy. But here's the really clever part. Star attention minimizes the amount of information that needs to be communicated between these hosts.
So they're not sending massive amounts of data back and forth.
Nope. During that final aggregation step, each host only sends a single scalar and a vector per token to a designated query host.
So it's like sending a concise summary instead of a bulky report.
Exactly. And that's thanks to this distributed softmax concept. It's what enables that streamlined communication between the hosts.
That's starting to make more sense. Now, this anchor block concept keeps popping up. The paper really emphasized its importance, but I'm still a bit fuzzy on how it actually works.
The anchor block is a really elegant solution to a common problem in long context processing. Attention sinks.
Attention sinks.
Yeah, it's like when you're trying to read a dense research paper and you keep getting sidetracked by footnotes or tangential references.
I know that feeling all too well. You lose track of the main thread.
Exactly. The same thing can happen in LLMs when they're processing these isolated chunks of text. Star attention solves this by prepending the first block of the context, the anchor block, to each of the other blocks.
So every host gets a copy of that first block in addition to its assigned chunk.
That's right. Because it strategically positions those attention sinks at the beginning of each chunk, where they're less likely to disrupt the processing of the actual information.
So it's like creating a controlled environment where those distractions are contained.
Precisely. And there's another benefit. Since the anchor block is the same for all hosts, it creates this shared point of reference. It ensures that their local computations are aligned with the overall context.
So it helps maintain accuracy even when you're processing information in this distributed way. That's pretty clever.
Yeah.
Now, the paper mentioned that the content of the anchor block is crucial, but its position within the sequence is less important. That seems counterintuitive.
It is surprising. You'd think placement would be critical, but their research suggests otherwise. They experimented with using a single repeated token, random tokens, even shuffling the tokens of the first block, but nothing performed as well as using the original content.
So the model needs that genuine taste of the global context, not just some placeholder or a shuffled version to really grasp the big picture.
It seems that way. It really highlights how nuanced these attention mechanisms are. There's still a lot we don't fully understand.
This anchor block is definitely shaping up to be a fascinating piece of the puzzle. But before we get too deep into the intricacies, I'm dying to hear about the results. Does star attention actually live up to the hype?
Let's dive into the performance metrics and find out. Well, the results are pretty impressive. On benchmarks like Ruler and Babylon star attention, consistently outperforms traditional approaches.
Okay, so we're talking real gains here, not just theoretical improvements.
Oh yeah, we're seeing speedups of up to 11x while maintaining accuracy that's comparable to full global attention.
Wow, 11x faster. That's huge. Did they test it on specific tasks or just overall performance?
They did both. They looked at those overall performance metrics, and they also tested star attention on specific tasks to see how it would handle different scenarios.
That's great. It gives you a much better sense of where it really shines and maybe where it falls short.
Right. One of the tasks they looked at was the needle in a haystack task, where the model has to find a specific piece of information buried within a massive amount of text.
Sounds like a nightmare scenario for an LLM.
It can be, but star attention excelled in this area. It really showed its strength in efficiently encoding and attending to those local contexts.
Which makes sense given its distributed approach. It's like having a team of experts, each one with their own specialized knowledge working together to find that needle.
Exactly. And it wasn't just about speed either. They found that star attention performed remarkably well on aggregation tasks, where you're summarizing information or extracting key insights from these long stretches of text.
So like summarizing a lengthy research paper or trying to get the main points from a complex legal document.
Precisely. It seems like that initial phase of local context encoding is really key here. By dividing the text up into manageable chunks and focusing on building that local understanding it effectively creates a set of concise summaries right from the start.
So it's almost like having each member of your research team summarize their chapter before coming together to discuss the overall findings.
That's a great analogy. It streamlines the whole process and ensures that everyone has a solid grasp of those key points before moving on to the bigger picture.
This is all incredibly encouraging. But I'm curious about those areas where star attention might face challenges. You mentioned earlier that it doesn't have explicit mechanisms for communication between those isolated context blocks. How does that impact its performance on tasks that require more global understanding of the information?
That's a great question. And it's a limitation that becomes apparent in multi-hop tracing tasks. These tasks require the model to follow a chain of reasoning across different parts of the text.
So instead of just finding a specific piece of information or summarizing a section, it has to connect the dots between multiple facts and understand the relationships between them.
Exactly. And because star attention relies solely on that global attention step in the second phase to tie everything together, it struggles a bit when those connections span across multiple blocks.
It's like each expert has a piece of the puzzle, but they can't directly talk to each other to figure out how those pieces fit together.
That's a good way to visualize it. And while star attention still performs decently on these tasks, there's definitely room for improvement. The researchers themselves acknowledge this as an area where more research is needed.
Interesting. It seems like understanding the limitations of an algorithm is just as important as celebrating its strengths.
Absolutely. It guides further innovation and helps us focus on those areas where we can make the biggest impact. And that's where those ablation studies become so valuable.
Right, those experiments where they systematically remove or alter specific components to understand their individual contribution.
Exactly. By testing different variations of the anchor block, for instance, they were able to gain a deeper understanding of its role and why its content is so critical for accurate processing.
Speaking of the anchor block, the paper mentioned this intriguing finding that it needs to be the same size as the other context blocks for optimal results. Any insights into why that might be?
It's a question that still has the researchers puzzled. It seems like the anchor block plays a more complex role than simply managing those attention sinks. There's more to uncouple there, and further research into its function could lead to even more efficient and accurate long-context LLMs.
It's exciting to think that there's still so much to discover and improve upon, even with these groundbreaking advancements.
Absolutely. This field is constantly evolving, and new insights are emerging all the time.
Now, you mentioned earlier that they tested star attention on the Babylon benchmark as well. This one focuses on tasks that require connecting information across multiple sentences, right?
That's correct. It's designed to evaluate how well LLMs can reason over long, complex narratives. And I'm happy to report that star attention performed admirably on these tasks, consistently achieving accuracy comparable to full global attention.
That's fantastic news. It suggests that star attention's approach might generalize well across a wider range of challenges, not just those focused on local understanding or summarization.
Precisely. However, there was one interesting anomaly they observed with the llama-based model on Babylon. It showed a significant accuracy boost at the 16K sequence length, but then a sharp decline at 128K.
That's unexpected. Any theories about what might have caused that?
It likely has to do with the nature of the base models. They haven't been specifically fine-tuned for instruction-following tasks, which are a key part of Babylon. This could lead to unpredictable behavior as the context length increases.
So it's like trying to run a marathon without proper training. You might get off to a good start, but eventually the lack of preparation catches up with you.
Exactly. It highlights the importance of choosing the right model for the right task. For instruction-following tasks with long contexts, the instruct models seem to be much more robust.
This has been an incredible journey through the world of star attention. We've covered so much ground, from its ingenious two-phase approach to the mysterious workings of the anchor block and those impressive performance gains across various benchmarks. It's clear that star attention is pushing the boundaries of what's possible with long context LLMs.
I completely agree. It's a remarkable achievement and a testament to the incredible innovation happening in this field.
But we can't wrap up without addressing the big question that's on everyone's mind. Could star attention or similar sparse attention mechanisms be the key to unlocking truly infinite context LLMs?
That's the holy grail, isn't it? Imagine a world where LLMs can seamlessly process entire libraries of information, connecting ideas across vast amounts of text without breaking a sweat.
It's a tantalizing prospect, and with research continuing at this pace, it might not be as far-fetched as it seems.
I'm incredibly optimistic about the future of this field. We're just scratching the surface of what's possible.
Well, I'm definitely feeling inspired to dive even deeper into this research. Speaking of diving deeper, the paper mentioned a GitHub link with the code for star attention. That's got to be a goldmine for anyone who wants to get hands-on and experiment.
Absolutely. It's a fantastic resource for researchers and developers who want to explore star attention in more detail.
I have a feeling we'll be seeing a lot more innovation in this area in the coming months and years.
I couldn't agree more. This is just the beginning.
Well, I want to thank you for joining me on this deep dive into star attention. It's been an enlightening and thought-provoking conversation.
It was my pleasure. I always enjoy exploring these cutting-edge developments with you.
It's amazing to think about the potential impact of all this. As these LLMs become more powerful and capable of processing so much information, where do you see star attention or these kinds of algorithms making the biggest difference?
Oh, wow. The possibilities are really endless. I think one area that has huge potential is scientific research. Imagine LLMs that can just devour entire scientific databases, connecting research papers, experimental results, theoretical frameworks, all at lightning speed.
It'd be like having a research assistant who's already read and synthesized every relevant paper in your field.
Exactly. It could totally change how scientists approach things like literature reviews, hypothesis generation, even experimental design.
Right. It could accelerate the pace of discovery by uncovering hidden connections or identifying promising research avenues that might have been missed.
Absolutely. And it's not just limited to science either. I can see this technology having a huge impact on fields like law, finance, even creative writing.
Oh yeah, think about lawyers who had to sift through tons of case law, or financial analysts analyzing years of market data.
Exactly. With these advanced LLMs, they could do that kind of research and analysis so much faster, freeing them up to focus on the higher level tasks.
Right. It's all about using AI to augment human capabilities, not replace them.
Exactly.
Now, with all this talk about the incredible potential of these advanced LLMs, we should also acknowledge the potential challenges and ethical considerations that come with them.
Of course. We need to be very mindful of potential biases that could be embedded in these models and ensure that they're used responsibly and ethically.
It's crucial that we develop robust mechanisms for auditing these models, ensure transparency in their decision-making processes, and address any unintended consequences that might arise.
Absolutely. Transparency and accountability are paramount. We need to make sure these powerful tools are used to benefit society as a whole.
Well said. This deep dive into star attention has been incredibly informative. It's also a good reminder that we need to approach these technological advancements with both excitement and a critical eye.
I agree. It's an ongoing conversation, and we need to be thoughtful about the ethical implications as these technologies evolve.
I'm really excited to see what the future holds for star attention and other groundbreaking innovations in the world of LLMs.
Me too. This is just the beginning.
To all our listeners out there, keep exploring, stay curious, and let's shape the future of AI together. Thanks for joining us on this deep dive into star attention.